Right, so I'm going to talk about synchronization even more. Hooray! Yeah, so usually I tend to be the only one bothering to talk about synchronization, so it's quite nice this time to have someone else do most of it. So I'm going to do some of what I usually do, but move on to something else towards the end. Still synchronization related. So the premise of how to do synchronization, you have lots of delicious work. Yum, 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 yum. And your GPU is extremely hungry. And ideally, you want to keep it fed all the time so that it keeps farting out pixels and keeps displaying pretty pictures on your screen. The issue is that now that Vulkan's here and DX12 and whatever else, you're kind of exposed to feeding it yourself, and you really don't want to get bitten by it. Lots of ways to trip up here. More concretely, the idea being that it's your job to keep in check what you're doing, when you're doing it, and how it gets transferred to the GPU, and you have to make sure you're not trying to stomp on anything the GPU is doing at the same time. And you want to give it a decent mix of stuff that it can get through at the same time. So on the keeping it fed side, the idea is that GPUs are hugely pipelined and parallel things, as Andrew was talking about a minute ago. Even within graphics, you've at least got a couple of stages there doing some work, and you'll see if you treat this as a flow from left to right, you can see that there's fragment work and vertex work happening at the same time. If you keep the pipeline filled, you get good utilization because you've killed both those stages and whatever other stages, and if there's any stalls for memory fetches or whatever, then the other stage that is not necessarily waiting on that can keep going at the same time. You might also have a compute queue or some other way of doing compute work at the same time as a separate stage, possibly other things like transfer and such. And ideally, you want to keep that filled with data as well. And the more stuff you can keep in there, the better you're going to have latency hiding. So synchronization, let's introduce a barrier. It's the weird bubbly thing at the bottom there in the compute queue. And let's say you add some work that barrier depends on. So here we've got completion of a draw call that has some tri-strip in it. Specifically, it's waiting on the vertex stage. Now, in this particular case, the GPU has not been scheduled enough work on the compute queue, so the barrier hits before the vertex stage for that particular draw call does. So you're now stuck waiting for that vertex work to complete. So by the time you actually get around to executing the vertex stage, the compute stage has just been sat idle, waiting around for this barrier to finish, and has not been doing anything. This is pretty much, well, this is what we call a pipeline bubble. It's a stall in the compute pipeline where there's been no work for no necessarily good reason, but it has been a stall. Once the barrier's been satisfied, obviously you can get going again, but you've still lost all that time where you could have potentially been doing work, and you may have underutilized your GPU in the meantime. Generally, it's a good idea to try and squash them as much as possible and have as few as you can. And the key way you do this is just by having more stuff front-loaded before you get to the barrier. Even with a pipeline barrier, even though it does necessarily wait, I kind of like to think of pipeline barriers as at least for the execution side, as a last resort. Ideally, by the time you get to the place where you're waiting the pipeline barrier, it should have already been satisfied. Otherwise, you end up with a pipeline bubble. Actually guaranteeing that everywhere portably is going to be very hard, but you can definitely submit more work to mitigate it. There are other strategies you can employ. So in terms of not getting bitten, the main deal here is that, as we've just seen, the GPU is doing a lot of stuff at the same time. And it's very easy to accidentally make two of those things disagree on what should be accessing what at the same time. And if you're not careful, you end up modifying some data that somewhere else is reading, or you might accidentally delete something on the CPU, then things are liable to blow up. You're liable to cause a crash quite easily by doing that sort of thing. So you've got to be very careful about that. If you don't, then you get lots of different things that could happen. You might get something very subtle, like image tearing. Sometimes that's acceptable. You might get complete image corruption. Everything might explode, might not render anything, which is always fun. Or arguably the worst possible case, everything looks fine until it's not. So, it's a tricky thing to do synchronization, particularly in Vulkan. Now you've been given, all of the reins. There's a lot of control in there, but a lot of responsibility as well. So what are you going to do about it? So first thing to do is understand what the heck you can do with synchronization. We've just heard from the Samsung guys about barriers and a little bit about subpass dependencies and very, very little bit about events. But there are these are the major types of synchronization you have in Vulkan overall. You've got pipeline barriers, events, and subpass dependencies. These are all sort of within command buffers, so they're fairly fine-grained in terms of what you're synchronizing with what else. You have semaphores, which if you have multiple queues on the system, say a transfer queue and a compute or graphics queue, then you can synchronize operations between those with semaphores. It's the only way to do that. And then getting from CPU to GPU, you have submission and fences to come back. A lot of people don't think of submission as a sync thing, but I'll explain why I choose to do it that way in a second. So I'm not going to talk much about pipeline barriers and subpass dependencies, in fact not at all, because we've just covered that. Events got covered more than I expected them to, but I think the way to think about them is that they're very similar to pipeline barriers, but they operate over a range. I know Andrew said one thing about what events are for, but I just thought I'd pop up my diagram that I'd already done before I saw his slide. The idea is basically you set where you're going to start the event, being satisfied, then you can submit additional stuff in the middle that's completely independent, and then you can have your dependent commands at the end to where you actually wait for that event. The idea here being that any work associated with an event, such as cache flushing or layout transitions potentially, or even just actually inserting stuff to actually perform the set of the event, can overlap with whatever you've set in the middle. You still get overlap with pipeline barriers if you do it correctly, but this gives you an extra dimension to be able to do that with. In terms of talking between two different queues, semaphores are sort of what you want. These are fairly coarse. You have these things in the spec called batches. For command submission, you get a VK submit info, which has an array of command buffers inside of it. And you can associate some number of semaphores to be weighted and some to be signaled within that batch. Similarly, you have things like present and acquire or sparse operations, which also will take a semaphore in a similar fashion. One thing that's not necessarily obvious unless you've been dealing with this for a while is that the GPU caches will be invalidated whenever you have a semaphore wait, or in Vulkan parlance, that's available writes are made visible, which has some implications in terms of, I think Fred talked about this a bit, where you have, you can avoid doing some work at a pipeline barrier time if you know a semaphore has already invalidated caches. And then submission. So I said this is a sync command. It kind of is. It's sort of a weird one in the sense that it's impossible to start work. It's sort of like until you put it in, there's an implicit barrier, and when you put it in, there isn't anymore. That's probably a strange statement to say. But the idea is the GPU can't do any work until you tell it to start doing work, right? There's kind of a blocker there, and the submission is sort of the satisfaction of that blocker. It's a weird way to think of things, but it makes more sense when you treat it in tandem with fences. So fences are the opposite way around. They sort of trigger once a piece of GPU work is finished, and then you can basically determine on the CPU when that has happened. The idea being there that you can sort of bounce back and forth between what's happening on the CPU and GPU. And this is pretty key for resource management. So these are both very coarse. It's a selection of batches, in fact, so multiple submit infos. The reasoning why that split exists, I'm not entirely sure, but it is there. But typical way to think about it is, say, one frame of rendering. So you might have, for a given frame of rendering, a set of resources associated with that and an amount of memory. In order to avoid stomping between frames, you tend to keep them separate for various resources. The idea is that once the fence has completed and you see that on the CPU, you can then reuse that set of memory and resources for another frame. So in this particular case, frame 0 used a set of resources, submitted it to the GPU is finished with it, tells the CPU via the fence, and at that point the application knows, right, well, I can reuse those resources because the GPU is no longer talking about them. And this is kind of good because you can batch everything. You don't have to talk about in terms of tracking individual resources between frames. You just say that frame's entire resources, which is something that was very hard and tricky to do in an implicit API like GL for a driver to do it. So there's quite a big win there potentially. There's also two massive stalling operations, device wait idle and queue wait idle. They're a huge sledgehammer. They basically just sit on the CPU and wait until all the GPU work is complete, either on the entire device or just on the queue that you specify. They are useful for teardown. In particular, once you've finished rendering, your application is quitting. It's a very quick way to go, I don't care about tracking anything, just wait and then delete everything, which is perfectly good use for it. But don't use it for anything else, for God's sakes. It is slow as hell. If you try to put that in the middle of a frame, you're in for a bad time. We saw that for a while, particularly with a few driver bugs floating out in initial Vulkan implementations. Except, again, debugging. Debugging's fine. If you want to use it to debugging, it's quite useful. So these are sort of the programmer guidelines I've usually given out with these talks. Now I will go through them, and they still apply. I've actually sneakily removed one, but we'll see why in a bit. First things first, specify exactly the right amount of synchronization, which is a pain, but that's the ideal that you want to try and get to. If you do too much, you're going to introduce too many pipeline bubbles and risk starving the GPU. And if you miss any, then you'll get things going wrong, potentially, with data being accessed at the wrong time or whatever else. Pipeline stages in particular are quite important. Again, as Fred sort of went through, and Andrew, those are kind of the key bits, particularly, again, yes, on mobile, but still important on any other GPU. Image layouts as well, again, Fred went through those in terms of compression. Render passes, useful for planning stuff ahead because the driver can actually get a sort of scheduling view of what's happening. One nice thing to be able to do there is if you have multiple independent renders, such as different shadow map passes, you can put them all into the same render pass without a dependency, and that, in theory, lets the driver actually not care about how they're scheduled together. It can just do them in whatever order it wants, which can save some time. Pay attention to implicit dependencies. So submit and semaphores both have some amount of cache invalidating associated with them. You don't want to be accidentally doing that again when you hit a pipeline barrier in a command buffer. And finally, and this is the most annoying one, there is different behavior depending on the implementation, and it can vary wildly. Tiling versus not tiling is a key example of that, but there's so much more. And so, unfortunately, you are going to have to test and tune about it on basically every single implementation you care about. There are, however, finally, some tools that have gotten a bit better to make that slightly less painful. It's not great yet, but it's certainly a lot better than it was a year ago when I gave this talk last. We definitely know it's an issue. Various things have happened, and things are getting better. So what I'm going to do now, this is the new part of my talk, is actually go through a few of those things and sort of give a little bit of advice on tooling. So first, most obvious one, validation layers. They do actually catch some stuff now, hooray. One of the main pain points we found, and I'll go into this a bit more in a bit, is with the combinations of enums you have to use. Which access flag goes with which pipeline stage goes with which layout. It's kind of hard to commit to memory and hard to recall, and developers seem to run into this quite a lot by getting it wrong. I think it's gotten better as education has gotten out there, but it still happens. It's quite easy to screw it up. Even naively, I will do it if I'm trying to write a barrier and end up having to read the spec to figure it out, which is great fun. The validation layers will now actually catch that sort of error very trivially. There was a lot of work sometime last year, I think, to make sure that happened. So that's great. There's also things to catch stuff like using graphic stages on a compute-only queue. I believe that's caught now. And there's also some sort of conservative amount of general misuse being tracked now as well. It's not going to capture everything. There's definitely still a lot of scope to do things wrong that it won't catch, but it's going to catch the most obvious ones, which is most of what you're going to run into anyway. If anyone has, particular problems with this stuff, please shout. The more people yelling about it, saying it's a problem, the more will get fixed. Of course, that's general to everything. If there's anything that's a problem, raise an issue, please. The next sort of set of things that have come out, profiling tools. I mean, they've been around for a while. They seem to have gotten better, actually, just over the course of Vulkan's lifetime, somewhat independently. But obviously, Vulkan integration has started happening with a lot of these tools as well. These are more useful for detecting over-synchronization in terms of figuring out when stalls have happened within the pipeline, if you've got unnecessary layout transitions or other unnecessary synchronization. You're more likely to be able to spot that with the profiling and tracing tools. Most of this is going to be stuff you're going to have to do vendor-specifically. I've put RGP up there for AMD GPUs, which does quite a lot of stuff, and I haven't looked at many other tools, unfortunately, but at least this one will give you quite a good breakdown of synchronization happening on the system. RenderDoc now has some vendor profiling integration with a couple of vendors, I think, at this point. And it can be used as a catch-all to a degree, but first and foremost, playback when it does after it does a capture will affect the results, which isn't ideal. And you still need to run it on each vendor platform to actually see the effect. So it's not necessarily a catch-all, but it can help with some very small class of issues, and you should probably be integrating into your pipeline anyway. Examples, there's a lot more rich set of examples out in the ecosystem today. Plenty, some even in the spec, not very many though. Just have a look, there's loads out there. More helpfully though, actually, there is actually a full page of synchronization examples, at least some of the common ones there. That link, I'll leave it on screen, but obviously I believe the slides are distributed afterwards as well. Alon, I assume we're selling out the slides after, yep, we are. Okay, it's on the Vulkan Docs wiki. I think it's actually the only page on the Vulkan Docs wiki at the moment, but it's there. If there's something missing, and I know there are some things missing, there's a to-do list at the bottom, and you want to see it added, raise an issue, and hopefully someone will do it. Maybe it'll be me, maybe it'll be someone else. And then the last thing, this is something I sort of developed after smashing my head against lots of developers asking which freaking enums do I use with which freaking enums. This is a sort of single header library, and the idea is to make synchronization for those fine-grained primitives a little bit easier. It still expresses most of the flexibility of what's on top, with only a little bit of the complexity. Although mileage may vary, there's still bits that might be missing. Last comment there. Yeah, DX12 developers might be more familiar with the syntax. It sort of has usages instead of actual sets of enums. It's not a one-to-one match with DX12, but it is more similar if you're used to that. So it is still hard, it's still explicit, but in theory this will help. So what actually it does, so I've mentioned before, these three stupid enums, people bang their heads against a lot because they look like this. Huge lists of things, each one has lists of things, and it's invalid to use certain things with certain combinations or nonsensical. So they're all interconnected in non-obvious ways and quite sparsely. And don't forget image layouts as well. It's a friggin' mess. I initially, when I first started looking at synchronization, was like, oh, this is fine, I completely understand this model. And then I started talking to developers about it, and then suddenly realized what sort of horrific pain there was around this. I would say these arrows should actually be correct. There might be a couple missing, but they're correct as far as I know. There shouldn't be a wrong one among them. So the whole point of this single-headed library is just to reduce the complexity, basically. Take those three ridiculous sparse enums and take them into one, which is a lot easier. So it seems like a fairly trivial thing to do, to just do a mapping, but it's if you haven't looked at these things yet, it's hard to overstate how bad it is. You end up just repeatedly looking at the spec to try and figure out what you're doing and making sure you're doing what you're doing. Obviously, validation layers now catch that stuff, which makes things better, but that's still a whole cycle of typing it in, running your app, seeing if it works. Oh, look, it broke. Where did it break? Why did it break? Look at the spec. Blah, blah, blah. It's been a huge pain in the arse. I've heard so much feedback that it's annoying, which is what's sort of spawned this thing. So in theory, it's a good thing to use if you're starting to tackle synchronization to start with. Now there is a disclaimer, it is still alpha software, which means something. Status-wise, mappings are all solid. If there is a mapping there and it says a thing, it has the right combination of enums under it to do the right thing. So you can absolutely already use it as a reference. If something's missing, please raise an issue. Someone found a sort of slightly edgy case the other day that isn't covered, which I'm going to try and get to soon. But for the most part, most of what you want is there. The interface may change. I haven't entirely settled on it. Functionality might get added or whatever. And I have had some success with one app integration already. I'm not sure I can actually name them, so I won't. But at least I worked with one developer to make sure that it worked. And it seems to, at least it goes through validation layers. Well, that's screaming, which is a good start. if anyone is interested in integrating this into an application, rather than just going ahead and doing it, please feel free to ping me. Either talk to me today or email me or raise an issue on GitHub and let me know. And I should be willing to help at least a little bit with that. Certainly willing to get engaged in the feedback for that. And it's, that website, that GitHub repo there, that's where it is if you want to go check it out. So programmer guidelines, they basically remain identical. None of that is incorrect. There was one I removed, which I doubt anyone spotted, but it was about validation layers, because I'm now replacing it with this one. Use all of the tools. There are a number of tools out there. They will help you. If you don't use them, good luck, which probably applies to most of Vulkan, actually. But synchronization, it's not completely, utterly terrifying. Once you understand it, it's not so bad. It then just becomes about the slog of actually making sure you're doing everything correctly, which is, what these tools are here for. And sorry that they're not great yet, but they are a lot better than they were, and they are still improving. And that is it. And I finished a little bit early, so I definitely have time for questions, if anyone has any.
Which guideline did you remove?
It was one about validation layers. It's just subsumed into the tools thing now. Anything else?
Should we get Ford vendors to start using subpasses?
Don't. No, that's not true. Subpasses. Oh, subpasses. Subpasses are fun in that they were kind of designed. I don't know how much I should go into now. I can rant about them a lot. I will say this. The actual practical use cases of subpasses are limited. The two that I usually recommend that should actually, at least one is kind of the best way to do it, which is for multi-sample resolve. That one just should be an immediate, just do it that way. Any other way is silly. The other one is kind of shoving multiple independent passes into one render pass. The kind of one that we originally touted it for, which was deferred shading, only really works if you're doing a very specific style of deferred shading that no one's really doing anymore, except Valve, I think, are still doing it that way. Basically, if you're doing any post-processing, you probably shouldn't be using them. Any post-processing that goes outside the current pixel. Anything else? Okay, thank you.